The plan for this lesson is to discuss statistical hypothesis testing for nominal or categorical data. We will start by setting up the stage where hypothesis testing fits into the scientific method. After that, we will discuss hypothesis testing procedure and explain the chi-square test for nominal data. In the scientific method, whether we're computer scientists, biologists, chemists, we start solving the problem by asking a question or seeing an observation. Then we do more research on the topic, make observations, and make assumptions to explain these observations. So that's when we get to hypothesis. We want to see if there is a relationship or correlation between two variables. So we make experiments to test these hypotheses, and based on the outcome, we take action. Testing space is a large topic. In this class, our focus is the nominal data type, and we will conduct the chi-square test. In the context of a statistical test, parametric methods are those methods that make certain assumptions about the underlying distribution of the data which we will use to draw a sample. And one big assumption is saying that this data follows a chi-square distribution, because if it follows this particular distribution, then we can apply the test and we can interpret the results. What is statistical hypothesis testing? So during the scientific method, we conduct experiments and obtain results. For example, testing the efficacy of a new drug or a new vaccine. Do these results have any statistical significance for the population? Or are these results due to random chance? So ultimately, a hypothesis test goal is to make a decision about the population based on a sample data using two complementary hypotheses, the null hypothesis and the alternative hypothesis. The null hypothesis assumes that there is no relationship between two variables. For example, age has no effect on music ability. So what we're saying here is age and music ability are not correlated. On the other hand, the alternative hypothesis contradicts the null hypothesis and states that there is a significant relationship between the two variables. So we might be able to achieve some progress by rejecting the null hypothesis and adopting this alternative hypothesis. However, if we are not able to reject the null hypothesis, this tool may not be able to make any progress because there isn't any statistical evidence. Statistic, which depends a lot on the data types and the context of the experiment. But as I explained earlier, we are going to focus on the chi-square test. The significance level, often denoted by alpha, is a threshold for deciding whether the observed data provided sufficient evidence to reject the null hypothesis. Calculating the test statistic from the observations is a straightforward step using a formula. And finally, we calculate the p-value, then use the outcome to either reject or fail to reject the null hypothesis. As a motivational example, we will work out the coin tossing problem. In this formulation, suppose that we tossed a coin 400 times and observed 54 heads and 46 tails. Is my coin biased? We need a statistical hypothesis test because we already know that the expected behavior should be 50-50, but we are seeing 54 and 46. In hypothesis testing, we frame the problem as a test statistic that follows a known distribution, which is the chi-square distribution in our case. In other words, we will convert the observed data, which is the 54 and 46, into a test statistic that conforms to the chi-square distribution under the null hypothesis. Let's take a moment and work on understanding the chi-square distribution. This graph shows the chi-square density function for various k degrees of freedom. But what is the meaning of degrees of freedom? Think about any problem formulation. There is always going to be a number of independent pieces or values or categories that are free to vary while we estimate the values of other parameters. For instance, in the coin tossing problem, once we know that we have 60 heads, it becomes clear that is going to be 40 tails. So the number of degrees of freedom in this case is 2 categories minus 1, which is 1. For the case of contingency tables, the number of degrees of freedom are the number of rows minus 1 multiplied by the number of columns minus 1. A chi-square distribution with k degrees of freedom is formed as sampling from the normal distribution with mu equals 0 and sigma equals 1, square the samples and sum them up. And as you can see in the graph, when k equals 1, the graph has this fast decaying behavior because it's just one squared normal distribution. But as the value of k increases, we start to see how the peak of the distribution starts to shift towards the right. Back to the coin tossing problem, the null hypothesis states that the coin is unbiased and the expected behavior is 50-50, and the alternative hypothesis contradicts the null hypothesis and states that the coin is biased and the probability is different than the expected behavior. For this problem, we set up alpha as 0.05. The next step is computing the test statistic, which is straightforward. So we take the sum of observed minus expected squared over expected, and for 54 heads and 46 tails, this means 54 minus the expected 50 squared over 50, then 46 minus 50 squared over 50, which is going to give us 0.64. The significance level is the probability that the deviation happened by random chance. And we typically set up alpha as 0.05 or 0.01, depending on the problem formulation. So to help you connect the dots, in the previous slide, we computed the test statistic, which is the 0.64. I'm going to use it to obtain the p-value, then I will compare it to alpha. If the p-value is less than alpha, then we reject the null hypothesis, and if it's greater, we fail to reject it. In other words, rejection means that there is enough evidence in the data that we can reject the null hypothesis. What is p-value and how to obtain it? The statistical test we computed in the previous slide quantifies the difference between the observed frequencies and the expected frequencies. Now, the p-value is a probability of obtaining a chi-square statistic that is at least as extreme as the one computed from the data, but with a very big assumption, which is the null hypothesis is true. And there are several methods to obtain the p-value for chi-square distribution with k equal 1 degrees of freedom. The first method is using the chi-square density function. So I'm going to look up the curve where k equals 1, and on the x-axis c 0.64 lies here, and integrate the area under the curve, which is really not the easiest way to go about it. Another method is using the chi-square cumulative distribution function. So for k equal 1, I'm going to look up the value where x less than or equal 0.64, subtract it from 1, and we get 0.4237. A more direct method is using the chi-square p-value plot, which pre-computes the p-values for different k's degrees of freedom and different test statistic. So all what I need to do here is to look up the value of 0.64 in k equals 1 curve, and we get the same value, which is the 0.4237. Finally, the most straightforward way and easiest of all is writing a Python script. All what we need to do is passing the observed frequencies and expected frequencies to the chi-square function, and in return we get the value of the test statistic, which is the 0.64, and the same p-value we looked up earlier. So now back to the coin tossing problem. We know that the p-value is 0.4237, which is greater than the threshold of 0.05, which means we fail to reject the null hypothesis because the observed data is not really sufficiently surprising under the null hypothesis. In this example, we have an exam with 100 questions, A, B, C, and D, and we would expect that the answers are distributed uniformly with 25, 25, 25, and 25. However, when we did an experiment and observed the outcome, we found a slightly different distribution with 20, 20, 25, and 35. So we want to make a statement that the answers are not uniform, and we want to formulate a hypothesis test. So the null hypothesis is going to say that the answers are uniformly distributed. The alternative hypothesis will contradict it and say this is not uniform. We set up alpha to 0.1, and we have degrees of freedom equal 3 because we have 4 categories minus 1 equals 3. So for n equals 100 and observed and expected frequencies in the table, plug in the numbers to the formula, we get 6. And to look up the p-value, it's straightforward. We're going to find k equal 3 with x-axis of 6. We find out that the p-value equals to 0.1116, which is greater than 0.1. And again, we fail to reject the null hypothesis. In this third problem, we have two nominal attributes, gender and preferred reading, and we're trying to figure out whether these attributes are correlated or not. The data is presented as a contingency table with the different configurations of each variable. Also, we have to compute the expected values by ourselves given the data. So for male and fiction, we are going to multiply the total of males, which is 300, by the total of fiction, then divide over 1500, and this is how we got the 90. And we do the same for the remaining cells. Computing the chi-square statistic is still straightforward, so we are going to find observed minus expected squared over expected and take the sum. In this case, we get 507.93. And in this problem, we have 1 degrees of freedom because we have 2 rows and 2 columns. 2 minus 1 by 2 minus 1 is still 1. And we look up the p-value, and it turns out to be a very, very tiny value. As you can see here, 8.7258 by 10 to the power minus 112, which is like really a tiny value. So the p-value is less than alpha, so we reject the null hypothesis. In summary, we covered the statistical hypothesis test for nominal data, and we worked our way through hypothesis testing procedure, where we focused on the chi-square test for nominal data.